In this video, I will walk you through free response question number 3 from the 2011 AP Calculus exam. This problem is mostly about area and volume. Let R be the region in the first quadrant enclosed by the graphs of f of x equals 8x to the third power and g of x equals sine pi x, as shown in the figure above. Part A. Write an equation for the line tangent to the graph of f at x equals 1/2. Whenever they ask us to write an equation of a tangent line, we like to use point-slope form, which reminds us that all we need is a point and the slope in order to write this equation. They gave us the point of tangency, so half of the problem is already done. The point is 1/2, 1. All we need now is to find the slope at this point. But we know in a calculus class, if we want to find the slope, we will use the derivative. So let's find f prime, and then we will evaluate it at x equals 1/2. So f prime of x. This is going to be 24 x to the second power. Now, what is f prime at 1/2? That will be 24 times 1/2 to the second power. Therefore, f prime at 1/2 is equal to 24 times 1/4. But this is just 24 divided by 4, which is 6. So this is the slope of f at 1/2, which is what we were looking for. Therefore, we can write the equation of the tangent line. Using this model, it's y minus y, so y minus 1, is equal to the slope, which is 6, times x minus x, which is 1/2. Let's make a sentence out of it. The equation of the tangent line is y minus 1 equals 6 times x minus 1/2. Part B. Find the area of R. If you integrate with respect to x, you can find the area between two functions by integrating the top function minus the bottom function. In this case, the top function is sine of pi x, and the bottom function is 8x to the third power. So here we are integrating the top function minus the bottom function. Region R from left to right goes from 0 to 1/2. So these are the limits of integration. I'm noticing that we have to do some u substitution to integrate the sine of pi x. Because it's not just x, it's pi x, we will do some mental u substitution. We don't need to do any u substitution on the second term, so I think it will be easiest if we split this up into two separate integrals. As we integrate the sine of pi x, technically I'm going to be doing u substitution, but I'm not going to show all of the steps because this is something we would do mentally. Imagine that we let u equal pi x, then u prime would just be pi. Whenever u prime is a constant, all that changes when we do the u substitution is that we end up dividing by that constant. So that means we're going to end up with 1 over pi in the front. So now I can just go on and find the antiderivative of sine u. The antiderivative of sine u is negative cosine u. So that's the antiderivative. Of course, this is a definite integral, so I would like to apply the limits of integration from 0 to 1/2. Now, moving on to the next term, I see that x to the third power, I'm increasing the exponent to 4, and dividing by that 4, 8 divided by 4 is 2. And again, I will apply the limits of integration from 0 to 1/2. Looking at the first term, I need to find the value at 1/2 minus the value at 0. When I evaluate a definite integral, I like to leave the constant out in the front. So here is the value at 1/2 minus the value at 0 for the first term. Similarly, for the second term, I'm going to leave that -2 out in the front. So here is the value at 1/2 minus the value at 0. The cosine of pi over 2 is 0, and the cosine of 0 is 1. 1/2 to the 4th power is 1/16, and we bring down the 0. -1 over pi times -1 is positive 1 over pi, and 2 times 1/16 reduces to 1/8. So the area of R is 1 over pi minus 1 over 8. Part C. Write, but do not evaluate, an integral expression for the volume of the solid generated when R is rotated about the horizontal line y equals 1. When you rotate region R around the line y equals 1, it creates a solid that's like a sideways bowl with a funnel carved out of the left side. When you take a slice of the solid, it forms a washer, a disc with a hole in it. We can use washers like this one to find the volume of the solid. It's a 3-step process. Step 1 is to find an expression for both radii of the washer. We will need an expression for the radius of the outer disc, which I will call big R, and we will need an expression for the radius of the inner disc, which I will call small r. Let's start with the big radius. Since the radius is vertical, we can find an expression by subtracting the top function minus the bottom function. In this case, the top function is 1, and the bottom function is 8x to the 3rd power. Now let's find an expression for the small radius. In this case, the top function is 1, and the bottom function is the red function sine pi x. So that's the end of step 1. We have an expression for the big radius and the small radius. Step 2 is to find an expression for the area of a washer. You can visualize the area of a washer as the area of a big disk minus the area of a small disk. In other words, the area of a washer is pi big R squared minus pi small r squared. Since we already have an expression for big R and small r, we can transform this into an expression for area by writing pi big R squared minus pi small r squared. The last step is to find an expression for the volume of the solid by integrating the area of a washer. Since we already have an expression for the area of a washer, all we need to do is integrate this. When you integrate the area of a washer, you are adding up all of the washers to form the solid. Since the washers are stacked up from left to right, we will integrate with respect to x. And since these washers are stacked up from left to right from 0 to 1/2, then these are the limits of integration. They only asked us to set up the integral expression, so this is the answer. The volume of the solid is given by this expression.